Greetings and welcome, friends. What wonderful weather we're having. Solving multi-step equations is what we're talking about today. So let's just jump right into things. The one thing I'd want to point out is, SAD mapping. We're undoing the order of operations. I like to think about isolating the variable that we're trying to get by itself here. It's kind of like disarming a bomb, perhaps, right? I want to undo all the stuff that's happening to it. So if I look at this particular equation, I'm gonna rewrite it a little bit larger. It says 2x minus 1 all over 3 is equal to negative 5. So what's happening in the world of x? First, it's being multiplied by 2, then it's being subtracted by 1, and then it's being divided by 3. So I'm going to have to undo things in that reverse order, right? Because I'm using inverse operations. The only way to undo dividing by 3 is to do what? Multiply by 3. So let's since divide by 3 was the last thing that happened to x, let's undo that thing first. So I'm going to undo that by multiplying both sides by 3. A perfectly legitimate move using the multiplication property of equality, which says if you multiply both sides of an equation by the same number, it's still going to be equal when it's all said and done. And notice that it does in fact undo that divide by 3, and we're one step closer to getting x all by its lonesome. Let's see, negative 5 times 3 is negative 15, of course. So let's see, what do I have to undo next? Well, multiplied by 2, subtracted by 1, what should I undo first?
Negative 1.
Yeah, we want to deal with a subtract 1.
Plus 1.
And we add 1 to both sides. Perfect, perfect. Notice how I'm lining up my like terms when I do my work, right, when possible. I've got my equal signs kind of all in this vertical column. Negative 15 plus 1 is going to become less negative, so it's negative 14. Well done. And then lastly, we would just do the plain old divide by 2, div by 2. Sorry if my 2's look like z's. If they were z's, I'd put a little slash through them, just so you know. So x is equal to negative 7. So that's how we would isolate the variable, right? I SAD mapped, I reverse PEMDAS sort of thing is what happened. Now, let me just show you real quick what a check looks like. And when we do a check, basically what it's saying is I'm going to now replace this back into the variable in the original equation and just verify that it works. Okay? So instead of 2x, I'm going to write this as 2 times negative 7 minus 1 all over 3 equals negative 5. And just a note about checking, don't solve when checking. Use PEMDAS. Okay? Because if I ended up solving again, like say I'm like, oh, I'm doing a check, I'm going to multiply both sides by 3, I could end up like repeating exactly the same thing I did over here, and it might not actually expose or reveal what my mistake was. All right, so it's not actually serving as a check if that's the case. So I'm just going to straight up order of operations this. All right, so the first thing that I got to do is the multiplication. 2 times negative 7 is negative 14, minus 1 all over 3, negative 5, right? And this, by the way, is what I call kind of a formal check where I'm plugging my answer back in to verify that it works, which is different than checking in the back of the book, which we're required to do on homework, right? Check with good old Bob, back of the book. Let's see, negative 14 minus 1 becomes more negative, so that's negative 15 divided by 3. Is that equal to negative 5? And technically, right, negative 15 divided by 3 is negative 5, but I wouldn't even make you write this last step. My rule of thumb for a check is as long as you bring it within just at most one operation per side, I'm fine with that. So I realize negative 15 divided by 3 is equal to negative 5, and if you want, you could even put like a nice little check mark. Look how awesome that check mark is. That's so cool. Yeah, that's pretty beast right there, that check mark. So so that's what a check would look like. All right, so let's do another example here. Make things a little bit crazier here. Cray, am I right? Let's see, so let me grab a nice little snapshot of this next problem, perhaps. Oh, this is going to be beautiful. Paste this right in here. And And here's our problem that I want us to solve. Actually, yeah, it's a good little problem here. So -3 parentheses. What operation's taking place there, by the way?
Multiplication.
That means multiplication, right? 2x plus 12, close parentheses, minus x equals 1. Huh. So this problem, we actually have like multiple x's hanging out here, which is kind of weird. What do you guys think we should do for starters?
I think we should distribute -3 into the parentheses.
I agree. Yeah, let's. Sometimes, in order to solve, the first thing you want to do is simplify. Okay, so we're going to do that. We're going to simplify this side. I'm going to multiply this -3 times everything in parentheses. And notice I'm not going to do this last distribution. That's, by the way, the sound effect that the eraser guy in Color Crew, a cool baby kids genius thing TV show that my son watches about coloring, says. Oh, fine. You don't even want to talk about Color Crew. I get it. That's fine.
I'm sorry.
Yeah. Well, let's see. -3 times 2x is going to be what? I'm multiplying here now.
-6x.
-6x. Yep. And -3 times 12. Well, let's see. It's going to be negative. 3 times 10 is 30. 3 times 2 is 6. 30 plus 6 is 36. Right? And then this -x, he's just like hanging out. Technically opposite x or something is what I should say. But so now, what should I do? I've got multiple x's still. I only want one variable by itself.
Okay, so
Combine like terms. I completely agree. Now, let me do a hypothetical wrong step first. Some students do this. What's wrong with that step?
you're talking about the same side of the equation.
They're not on the same side of the equation, precisely. Aha, perfect. Right, so they're already hanging out together. They're hanging out on the same side, so I don't need to like add x or add 6x to both sides. I can just combine these as like terms.
So
All right.
it just becomes -7x or just still -7?
Yeah, -7x, exactly. So when you're combining like terms, the idea is that you will add the coefficients, right? So -6 plus, technically there's a little invisible 1 right there. -6 plus -1 is -7. And the exponent remains the same. So these are x to the first. We'll talk more about exponents a little bit later. So it's like I had -6 apple pies and another negative apple pie. How many apple pies do I have? I've got -7 apple pies. They don't suddenly become like apple sundae ice cream a la modes or something. They're just still plain old. I'm just counting them. That's all it is. So now I've got a singular variable here. So now I can just solve normal, right? So you guys can go from here practically blindfolded, I know. So let's see. Add 36 to both sides. So -7x equals 37. And then how do I get rid of that -7?
Well, you can divide by 7.
Divide by,
Sorry.
yeah, better yet, -7. So I just want to point out some students get confused with the minus sign there and think that we'd add to both sides, but no, this -7 is being multiplied by x, so the undoing of it would be division. And let's see, 37 sevenths, I don't believe that reduces, does it?
It doesn't.
Yeah, so this is just a -37 sevenths. Notice I actually don't like leaving a minus sign in the denominator. That's kind of weird. So either put it out in front of the fraction or maybe in the numerator. Those would mean the same thing.
That's right.
So I'll point that out real quick. -1/2 is equal to -1/2 is equal to 1/2. But they are not equal to something like this, -1/2. That would not be right. Right? There's only one minus sign that's present. And the ones that I prefer are usually something like this middle one here is quite nice. So yeah, so that problem's not too bad. Not too bad at all. And if I wanted to do a check, which I won't take the time to, I just want to point out that I would actually have to plug this in everywhere I saw an x. So I would plug it in there and there. Aha. Intriguing. All right, so everywhere I saw an x would have to be replaced by that. All right, so that one had the same variable represented twice. Let's look at another one kind of like that. Let's see, a little snapshot right here. Snap. Oh, I like it. I like it. Here we go. Ooh, interesting. And hey, we're not using x's. I just want to point out variables, like we said yesterday, could be any letter. They don't have to necessarily be x's and y's and z's, which is typically what mathematicians use. So notice I've got some n's here on both sides of the equation. So the first move I want to do is bring them together. And my suggestion, the thing I like to do, is move the little guy to the big guy. Which the value in doing that is that it will avoid me having a negative number of n's. I mean, it's not technically super important, but that's, oh, sorry, that's a positive 5n, silly me. So this is what we got. So who is the smaller value of n? Which is smaller, 3n or 5n? 3n. So how should I move this 3n to the other side? Because I can't just combine those like terms, because they're not hanging out together. They're on opposite sides of the equal sign. Yeah, so to undo a 3n, that's kind of being added to this side, I guess you could say, we'd subtract 3n from both sides. And I think you agree that a 3n and a negative 3n would cancel each other out to be 0 n's, and 0 times n is going to be 0. So this will give me negative 1. Make sure we don't drop or lose our minus sign there. 5n minus 3n is how many n's? 2n plus 6. And now we can solve normal like subtract 6 from both sides. A negative and a negative is becoming more negative, so that's negative 1 plus 6 is 7. 2n there. And then divide both sides by 2. And I like to do the old flipperoo right at the end here, because I like my variable solved on the left side. N is equal to negative 7 halves there, right?
Wait,
What's your question?
I thought that negative 6 and negative 1 makes positive 7.
Nope. Multiplying two negatives become positive, but adding them, it's like borrowing $1 from your friend and then borrowing $6 from your friend. Your friend's not going to be like, oh, wait a minute. You now have like positive $7. Like, I owe you $7. Nope. No, we're even more in debt. So, yep. We'll do some more practice with those later. I've got some stories like that.
No, actually no.
No.
That would work out for Brandon.
Let's see. This is an example that I just added just before class. I think it's worth pointing out. We might just start it just to save some time, but there's so many different ways these problems can exist. But I figured like this looks enough different from the previous one that it'd be kind of be scary, right? All right.
A little scary.
So I guess the first thing I would say is simplify both sides.
So I just distribute both of them.
Yep, and then bring the x's together, or bring the variables together. Vars is what we would do. So let's see. I heard a good suggestion for simplifying here. It was distributing, I believe. So I can distribute this negative 2 to both of those guys and this 4 to both of those guys. So we can simultaneously do that, I believe, without too much difficulty. So negative 2 times x is negative 2x. Negative 2 times 4 is negative 8. Equals 4 times 3x. What's that going to be? 12x. Yeah, I just multiply the numbers and the variable stays the same there. 4 times 2 is 8. Aha. Okay. So we've simplified, and now notice that it's actually kind of similar to where we started here, where I had a variable on both sides. Same sort of idea there. And then what would I do to bring the variables together? Yeah, I'd move the little guy to the big guy. Add 2x is the only way to undo that negative 2x there, right? You guys agree that these would cancel each other out, which is what I want. So we'd get negative 8 is equal to, how many x's is that? 14x plus 8. And I'm just going to dot, dot, dot that with an ellipsis, because you guys know what to do from there.
Wait,
What's up?
But it's weird because if you add 8 and then add,
you'd have to subtract it and then you'd have 0.
No?
Yeah.
Maybe we will do this step then. Uh-huh.
Oh, they're both
No, you'd have negatives.
Oh, you have negative 16.
Right. Uh-huh. There we go. So right. So this is negative 16 equals 14x. Okay. Okay. We'll do this one. It's worth it. It's worth it. Divide by 14. And I'll get x equals, I'll do the old flipperoo right at the end, reflexive property of equality. Says if a equals b, then b equals a, so let's just rewrite it. 16/14. Both of those are divisible by 2. 2 goes into 14 7 times and into 16 8 times, so negative 8/7. Not too shabby. Good, good, good. Let's see. Now, so these are all plain old solving problems where we only had one variable represented. Okay, let's talk about formulas though, because sometimes in formulas, I'm sure you've seen formulas have like multiple letters in them. Yeah.
a little scary.
Yeah.
Yeah, it's a little bit different. So we're going to just do 2 quick examples on solving for a given variable within a formula. Okay? So I believe these formulas will be familiar to you. So let's say force equals mass times acceleration there for my Newtonian friends. So now this is a formula that's solved for force, all right? So if F equals ma, that's perfectly great if I happen to know the mass and the acceleration and I want to calculate the force. But what if I wanted a formula that calculates the acceleration if I happen to already know the force and the mass? Okay? So the fact that I'm solving for A, I'm now kind of pretending that A is my variable, and we're thinking of these just as like numbers, all right? Just like, so pretend it was just like, you know, one of the problems we did last night or today or something like that. So if I want to solve for A, what is currently happening to A? It's being multiplied by M. So how do I undo multiplying by M?
So you have to divide by m from both sides.
Yeah. So just pretend that this is like a number, right? If that said 2A, I would divide both sides by 2, right? And let's do a little flipperoo here, and I'd get A is equal to force over mass, right? And now I've just kind of reconfigured that formula for us, where it ends up being a formula for acceleration given those other 2 parameters, if you will, right? So that's not too crazy. It's just a little weird seeing more letters than numbers in a math problem, but it's okay. That's okay. Yeah, good stuff. Good stuff. Here, so that was a physics formula. Let's do a geometry formula, and then we'll call it a day. A day.
A day.
Oh.
Does anyone recognize this formula?
Yeah.
Recognize this?
Area equals half the triangle.
Nope.
It's
Half the base times height is area of a triangle. It's a 2-dimensional figure because it's area, not volume. Does anyone know what this represents?
Sphere.
No.
Rectangle? No. Trapezoid.
Trapezoid. All right, where I'd have base 1, base 2, and then another dimension being the distance between those 2 parallel sides, which I'd call h. All right. So this is the formula for the area of a trapezoid. But they said, let's make a formula that solves for
E1.
base 1. Yeah, that's what they're looking for here. So if A is equal to half the height times the sum of the bases, how do I get this guy by itself? So I've got to kind of reverse PEMDAS this. I'm just sad mepping it.
You have to distribute the one.
We could distribute. We could. But I'm actually going to get rid of this another way first. Because I realize this B1 has a positive coefficient. It'd be just kind of nice to not have to spoil it. So I'm just pretending I'm being multiplied by a half h. We could get rid of both of those in one step or one at a time. How would I get rid of multiplying by a half?
We divide by a half.
Or what's the mathematical equivalent?
Multiplying by 2.
Yeah, let's multiply by 2 first of all. So we'll just multiply both sides by 2. We'll get rid of one of those at a time. Technically, I could get rid of both if I wanted. So I'm going to find out that 2 times a, capital A, by the way. Notice that for many of our formulas, lowercase letters are actually used to represent linear dimensions, and uppercase letters are used to represent more complicated ones. So like a two-dimensional one here. So 2 times a half cancels out, right? So now I'm going to have h times b1 plus b2. How could I get rid of that h? It's currently being multiplied by our friend.
We could divide by h.
Yeah, divide both sides by h. By the way, your distribution idea at the beginning was not wrong. Definitely would have worked.
Are you still recording, Mr. Ryan?
Oh yeah,
Oh.
it's okay. So let's see. Aha, we're getting warmer, right? Because the h's would have canceled out over here. So how do I get b1 by itself? Yes, subtract b2. Right, so if I just kind of pretend that these are numbers-ish, we can be okay. Right, so I'm going to find that b1 is equal to 2a over h minus, oh, I just wrote b squared instead of b2, guys. How embarrassing. Let me fix that. How embarrassing. Completely different between subscript and a superscript. Oh my goodness. So here is a formula for base 1 of a trapezoid if you happen to know the area of the trapezoid, the height of the trapezoid, and the other base. All right, so we just are able to use these skills of, you know, moving things around in equations to even deal with things that have more letters than numbers. Crazy stuff, crazy stuff. And by the way, there is another way to do this. The other representation would have been something like this. 2a minus, would it have been hb2 all over h would have been another representation of it if you tried the distributive property method, which these are mathematically equivalent. It'd just be like if I tried to combine these as fractions and I needed a common variable LCD, right, sort of thing. But anyways, so there you go. Pretend they're numbers. Thanks for watching, Internet friends. Have a great day. Bye-bye.
Internet friends.